All right, let's go ahead and get started here, Scott. Thank you to everybody who's joining us on the webinar. We'll go ahead and just a little bit of housekeeping here as we get started. Um, One, as far as asking questions goes, there is a questions panel at the bottom of your screen there where you can ask questions, and that's the best way to get a hold of us and ask any questions as we go through here. Also, from a timing standpoint, we planned a half an hour for this. I think the original webinar said 1 hour, but we'll keep this to a half an hour and let everybody get back to their day. Um, so just to kick things off, a little introduction on who's on the call today. So my name is Kevin Jones, the Director of Sales and Marketing for the Data Park Group here at Capstone, and I'm joined by Scott Carey, who's not only an integration partner we've been working with for many years, but someone that is a fellow Vandal from the University of Idaho. So I'll let Scott give a quick introduction to himself, and then we'll get into soft sensors.
Yeah, thanks a lot, Kevin. Kevin asked me to join today. I actually am an independent contractor, run my own little company called Castle Mountain Technology LLC, but I've worked closely with Capstone for quite a few years now, both as a data park integrator and also doing a bunch of contract data analysis work. And in both of those areas, I've worked a lot with ParkView and specifically Park Model, which is what we're going to talk about today as a tool for developing models that can be used for soft sensors, among other things. As Kevin said, I'm a University of Idaho grad, chemical engineer. I've been working in the industry for about 14 years. Most of my experience has been in pulp and paper and also the sugar industry, but I've dabbled in a few other things a little bit as well. So I suppose from there, Kevin, shall we go ahead and dive right in?
Yeah. Thank you for the introduction there, Scott. So just before I hand it back to you, I wanted to just set the stage a little bit for the audience. Just talk a little bit about Data Park in general. We're talking about Park Model, which is our multivariable modeling tool specifically, but it is part of the larger Data Park application set. And one of the key things that the Data Park brings is the integration of all the data sources out there, whether it's your data historian, your lab quality, or other sources out there. And as Scott gets into his discussion on building soft sensors, that's no different. So we are able to leverage data no matter where it's located for building these soft sensors. So just wanted to take a step back and look at this from a big picture first before we dive into it. And then just peeling back the onion a little here, Park Model is our multivariable modeling capability, which has a couple of different statistical capabilities within it, but we're really going to dive into the soft sensor use case here and have Scott show us some examples he's done and some of the best practices when it comes to building these soft sensors. So without further ado, Scott, I'm going to make you the presenter here.
Okay.
You should have control. There we go.
Okay. So the first thing I want to talk about briefly is what is Park Model? And Park Model is a tool within the Data Park suite that's basically designed for building multi-input, single output models, especially linear models. And all of what I'm going to talk about today is the PLS modeling features in Park Model. PCA modeling is useful as well, but for developing soft sensors and for most of my experience, the PLS modeling tools are what are most useful. So that's what we'll talk about most today. And so in a PLS model, essentially you're taking a list, virtually unlimited number of input variables, and using data from the process to crunch through a bunch of math and determine how all those input variables affect a single output variable. And what you end up with is a big linear equation with steady state gains for each input variable as they relate to the output variable, and of course a y-intercept. So what kind of processes does this work on? What's it useful for? Typically we're looking at continuous processes, or I want to say repetitive batch processes, and what I mean by that is processes where you're running some kind of batch that's happening on a fairly fixed time interval, and it's producing roughly the same product all the time, over and over and again. If you have data that's aggregated for each batch, then it almost becomes a continuous process, and you can also do modeling with it. One thing you want to look for is a process that has a significant number of online measurements of the process input parameters, or the conditions of the input materials, and you don't have to have everything measured online real time, but the more of that you have, the more likely you are to be able to build a good real-time model. Also, and of course, this is where the model becomes so useful, is if you have periodic laboratory or analyzer analysis of process outputs. So I'm talking about, if you're continuously measuring the inputs, but your process output has a quality measurement that's only measured by a laboratory every 1 hour, 2 hours, 4 hours, then the beauty of a model like this is it allows you to calculate, to predict the result of that periodic analysis real time, and have real time feedback in between the sample analysis that the laboratory or the periodic analyzer runs. That's what's so powerful about it. Another thing to look for is parameters where the output parameter especially has a high, what I call signal to noise ratio. So we don't want a lot of random variability in the output parameter analysis, at least compared to the real variability, the longer term trends that you see in real changes in the process. Because obviously we can't model random noise. That there's no it's unpredictable. So we need signals that are relatively clean. Don't have to be perfect, but the cleaner the better. The other thing that we want to try to avoid is unmeasured disturbances to the process. So if we have some kind of major change to the input materials, for instance, to a process, and we don't have any indication or any measurement of that, it's gonna throw the model off if it doesn't have an input to account for that. But in most cases, we are measuring our conditions or our quality of our input materials, or whatever the case may be. So typically that's not a big problem, but you do have to watch for it. And the last thing to know is, and this is important, is that long process delays are actually okay in Park Model. Park Model has the ability to handle long process delays within the calculations and account for those. So it's not a problem if you have a long, input to output delay time in your process. Okay. So getting to the meat of the matter here, what's the process for modeling using PLS within Park Model? So what I'm going to do is I'm going to switch back and forth a little bit between this slide here that has the steps on it, and then actually showing you a demonstration building a quick model using Park Model. So the first thing we have to do is what process and what data are we going to use for modeling. So let me escape here. And what I've got right here is a trend of a continuous digester output kappa number from a pulp and paper mill. The kappa is a measurement of essentially how thoroughly cooked the wood is, how much of the lignin has been broken down in the fiber. So the lower the kappa number, the better it's been cooked. So this is it depends on the facility, but in a lot of cases, this is a measurement that's either sampled on a periodic sampler that's automatic, or even it's a manual lab sample that's run every so often. So this is something that would be very helpful to have a continuous feedback for if we had the soft sensor to do that. So what we need to do first is decide the time period that we're going to try modeling. And if you notice here, I have 211 days worth of data in this particular trend view here. That's a long time. A lot of things happen over 211 days. So typically for a soft sensor model, we want to narrow down a little bit more than that. And you can see the data quality actually gets better through the period. In the early portion of this data set, it appears to be a few more outliers, a little more noise in the data. But as we get past especially this point here in July, it looks like the data improves a lot. So I want to choose a section of this cleaner data that has enough variability so that I can actually model changes in the kappa, but is also clean and relatively stable with regards to outliers and shutdowns and things like that. So what I'm going to do is I'm just going to do, and for those of you that know PartView, all you have to do to zoom in on a time period is click and drag over it, right click and zoom. So now I have a much narrower time frame here that I'm working with. And what I'm going to do, just so I don't lose it, is I'm going to come in here, configure, and fill the times in for the trend configuration. So now the trend is basically saved with this time frame. Now the next thing I want to do, this is my output variable. The output variable always has to come first in the trend that you're going to use for park model. So it always has to be the top one in the list. And I need to tell ParkView that this is a manual sample tag. So I'm going to come in here and configure, and in the interpolation area of the tag configuration, I just want to set this to manual, and that tells Park Model whenever I build my model that this is a manual sampled tag, and that it needs to only choose the actual data points to model instead of trying to interpolate between data points. That's how you want to set almost every park model trend that you would build, is set your output variable as a manual tag. There's very few cases where you would want to try to model interpolation between actual data points. Okay, so let's go back to our list here. So I've selected the modeling period, and I want to build the ParkView trend with the output tag first. Okay, I've done that, followed by process inputs. Okay, so now we have to choose the process inputs, and this is where a little bit of process knowledge is typically helpful. That you want to know, in general, what input variables might affect the output variables. And you can always add more to your trend than what is actually needed. So I'm going to come in here, and I've got the tag browser set up to this, this process area. So let's go through, and for a digester, I just got to find my tags. Okay, so the alkali charge to the impregnation bin and the alkali charge to the digester, those are two parameters representing the amount of cooking chemical essentially that we're using in this process. So those are important, or I think they might be important. We'll find out more from Park Model. The relative H factor, that's a measurement of time and temperature. Again, should be important relative to cooking. The chip level, that again affects the residence time. So find the chip level. I think I passed it. There it is. Chip level in the impregnation bin and the chip level in the digester. And the calculated blow per ton. So this is just a measurement of the volumetric blow flow out of the digester per ton of dry pulp produced. And the residual transfer. So we have several residual alkali measurements. So this is an online sensor, essentially similar to a pH probe, but it's measuring the residual alkali in the liquid streams circulating around the digester. So we'll take the one for the transfer liquor, the upper extraction, lower extraction. Okay, so now I have a list of input variables that I think are at least likely to affect the output variable, which is the discharge kappa. And they're all trended here together, and the time span of this trend is important because the time span that you can see on the trend is the same time span of data that Park model will use. That's why we selected that period with a relatively clean kappa data, but enough variability to see some changes. And you can see that most of the input variables are changing as well. And that's important too, because if an input variable doesn't change, then there's nothing to model. There's no variation to see an impact on the output. One here that I can see that might not be changing a lot is this impregnation bin level, the blue plot here. There's a little noise in that, but for the most part, it looks like it's on a pretty straight line. So that one may not be affecting the output much, but we'll see. Okay, so back to our list. If the process output is a manual test, we did that already. We configured the interpolation as manual. So now it's time to open Park model. And once you have a Park model license, that's really easy. Just right click, come to the bottom of your right click menu on the trend and click Park model. And you get this menu, which allows you to open existing models if you have them already developed, which I have lots of them, or create a new one and several other options. And this create new PLS model is what we'll do. But before we do it, we need to check what it's calling interpolation here, which is really what time interval do we want the model to work on. So in other words, how many data points and how far apart should each data point be? And if there is a manual tag in the trend, which in this case our output variable is the manual tag, we set that earlier, then the interpolation will just match that manual tag. So for each manual tag data point, we'll calculate a prediction. If you select this step size button here, then you can manually set an equal interval for each prediction. But again, in most cases, you want to just stick with the manual tag data points for each prediction. Okay, so we'll go ahead and click Create New PLS Model and bring that over from my other screen. So immediately, as soon as you create it, Park model calculates the best fit model based on the outputs for the input. And this view that I'm showing right now is basically a time trend of the observed data, so that the black is simply the kappa that we had on the trend, just as it was. And the blue is the model prediction based on the input variables. And I haven't changed any settings. I haven't done anything yet. So this may not be as good as it gets, but this is the starting point. Park model calculates an R² value, which is essentially just a measurement of fit. A perfect fit is a 1.0 R². So this will always be between 0 and 1. And you can see even at a 0.368, which is less than half, it actually is a fairly decent fit. It's following the long-term trends pretty well. So we can also view this in a couple of different ways. We can look at a XY plot of observed versus predicted. So the Y-axis is the actual observations, and the X-axis are the predicted observations. And of course, the closer they sit to this one-to-one line, the more accurate the model is. In this case, we do have some scatter, so there's a little inaccuracy there. If you don't want to use a time trend, if you want to just use by observation number, you can look at it this way. Pretty similar in this case to the time trend. So there's a few other things to look at in this model. Scrolling down here, we have a list of the model variables. The Y is the model output, so that's the kappa. I'm going to go ahead and expand this description column. So the discharge kappa is the first one on the list. That's our process output. And let's say, for instance, that we don't want to look at any kappa data. Let's look at the trend here. Any kappa data greater than 16. Let's say that we know that anything over 16 is an outlier. We can come in here, type 16 in the max filter, and come back to the top, calculate. And now you can see that any points over 16 are eliminated from the list. and we've just recalculated the model by filtering those out. And you can do that with process inputs as well. So we could go down the list. Sorry about that. There we go. We could go down the list of process inputs, and if we know that any of these should be within a certain range, but you know, something's falling outside a range, we could filter that with the filter min and maxes, and it will just simply exclude data points that are outside that range. The other really important thing about park model, and really useful thing that I mentioned earlier, is that it can not only handle long process delays, but it can also help identify them. So let's say that you think there might be a process delay between the impregnation bin alkali charge and the kappa, but you don't know exactly how long it might be. Well, this trend right here can give you an idea of that. This is the variable correlation versus time lag analysis. What this does is says, okay, at time 0, the impregnation bin alkali charge is only slightly correlated, just barely above 0, to the outlet kappa, our output variable. But if I go out to a longer time in the future, I see that there's this negative correlation. And what we're looking for is the absolute value of the correlation, either positive or negative. But the bigger it is, the more impact it's having on that output variable. And so as you can see in the little gray box popped up there, as I drag along, it's telling me how far out in time that correlation is. Now, I know from process experience that it shouldn't be more than a day, so this is maybe a little long here, but I do see that, you know, at 12 hours, I've got a better correlation than I had at 0. So I can put in a lag here of 12 hours, and then come back up and recalculate, and the model changes a little bit. I didn't actually get any better in that case, so I might go back and try a different time frame. But the bottom line is we could go through all of these parameters and do the same thing. Like for instance, this relative H factor, this one has a really sharp little peak here at about 2 hours. So if we do 2 hours on that one and calculate again, now my R squared went up to 458. So I got a big bump in model fit. It's fitting a lot better now that I entered this delay on the H factor data. So that's telling me that yes, there's definitely a time delay between when the H factor changes and when the outlet kappa changes. And so I could go through all of them. I won't spend the time today to do that. But essentially what we end up with is a list of input variables, and both their importance and their coefficients. So the importance is essentially just a relative impact on the output variable. So what this is telling us here is that of all these input variables, the relative H factor has just over half of the impact on the variability of the output variable. So this is a very important input variable. The blow per ton comes next at just over 20%, and then on down the line until we get down to the chip bin, the impregnation bin chip level, only 2% importance. That's a very minor importance, and I might decide to actually eliminate this variable and rerun my model without it, because why include variables that don't have much impact? And I believe we saw that one earlier was the straight line on the plot. That's the blue trend here. So that's not surprising at all that without much variability in the variable, we're not going to see an impact on the output. The other thing that's important to know here is the model coefficients. So if I was to build an equation, a linear equation to describe the output kappa from this digester using these inputs, all I would need to do is start with a y-intercept of 20.5 and then multiply negative 0.065 times the impregnation bin alkali charge, negative 0.185 times the alkali charge to the digester. On down the line, each one of these are simply linear coefficients for each of those x variables, and you just sum all of those linear coefficients times their x variables in a long linear equation. It's actually pretty simple. So we've created the PLS model. We've evaluated the cross correlation trends for process delays and interlag times. We've dealt with min-max filters. You can also, let's go back to this. So there's some statistics that are calculated here in these two black trends below the fit trend. And what we're looking at is anything outside these green and red, especially the red lines, are probably process outliers that might be throwing off our model. So what we can do, it's real simple. Just click and drag over a point that we don't like. And you can't see me, but I'm hitting the delete key right now. And when I do that, it eliminates that data point from the model and excludes it from the calculations so that we're not using outlier data for the calculation. So you can use these filter min and maxes over here, or you can simply click and drag. I'll do another pair of them here that are pretty far out, delete, and now the model is not accounting for those outlier data. So really quickly, whenever we finish with this and we're happy with the model, we want to save it. And we can save with a name, demonstration, kappa model. And what that does is that saves this model to my ParkView database. Now, if I come to my trend and come into my tag browser, I can go to the data source called Park Model, and I'll need to search. Okay, so this is my model I just created. I put this on the trend and set up the range to match the input variable. So let's turn off all the others. So now you can see the calculated value trending alongside the actual value. Now this was during the modeling period. Let's say I want to see how this model performs outside the modeling period. Well, now all I have to do is go ahead and scroll over. Now everything past August 3rd is period that was not used in the modeling, but is simply the performance of the soft sensor prediction going forward. And you can see it continues to predict pretty well. So that's really useful that ParkView just already builds that tag with the model output that you need, and you can just simply drag and drop it onto trends as any other tag. All right, we're running a little short on time. I think I'm just about finished. So what are these models useful for? Obviously the big one and what we're focused on today is soft sensors. So if you have a periodic test, whether it's from a lab test or a sampler and an automatic analyzer that runs on a schedule, you can use these mathematical models, these PLS models, to build a real-time feedback soft sensor to give you information between those test samples. And the real money in that is, of course, being able to build real-time closed-loop control of a parameter that was tested in the lab. That's the kind of the best use case scenario, I would say. And then there's other things that are valuable as well. You can quantify the linear relationship between inputs and outputs. One example I've used it for in that case is on a steam turbine with a steam turbine generator with multiple extractions. If you want to know how much electricity is produced for each pound of steam at different extraction points, you can use a PLS model, and then the linear gains that are produced by that model will tell you how much power you get for each pound of steam at each extraction point. You can evaluate process predictability and repeatability. So one thing that's interesting is to look at, for instance, an O2 delig plant in a paper mill and see whether the outlet kappa is predictable by looking at the inlet kappa and some other parameters like temperatures and alkali charge and those things. If the outlet kappa is predictable, then you know it's probably controllable. But if for whatever reason the outlet parameter doesn't show any correlation to any of the input parameters, in other words, the PLS model doesn't fit, then you know that you're missing an instrument, you're missing a measurement, or there's a measurement problem somewhere. And that kind of leads to this last use case, which is online and automatic sensor validation. So in some cases, you might have a sensor that needs maintenance on some basis, and you know at times it drifts or it stops working. Well, if you have a soft sensor running in parallel to that online sensor, and all of a sudden you see a big shift in the online sensor, but the soft sensor is still similar to what it was, then you know that the online sensor may have a problem. So you're just using the calculation to validate it, and you can alarm off of that difference and then do some maintenance or whatever's necessary. So with that, I think we'll try and wrap up. I know that was pretty fast, but I'll just watch the chat window here for any questions just for a moment. Kevin, do you have anything to add?
No, that was great, Scott. A couple of questions that I wrote down here as we were going through it. Maybe we can go through a few of them before we adjourn here. The first one I had is, so when you built that model, you're looking at about 20 days of data. Do you have any recommendation on, what is the frequency of data someone would need to build this model, and what kind of a time period they would need to effectively build a model? Any kind of best practices there?
In my experience, it really depends on the number of output data samples that you have. So let's say that you're modeling something that's only sampled, say, twice a shift,
Yep.
once every 4 or 6 hours or something. In that case, you need a fairly long period of time, because let's say you're modeling using 10 process inputs, then you probably want 1,000 data points in your model.
Okay.
So of course, if you're only sampling a few times a day, that's several hundred days.
Right. So if you need a
Whereas
thousand
if
data points and you're only sampling twice a day, you need 500 days to get those 1,000 sample points.
Exactly, so that it's kind of a ratio of how many data points you need versus how many input parameters you're using, because in the worst case scenario, if you had 50 input parameters to your model and you had 50 data points, you would always get a perfect R squared of 1.0, a perfect model, even though you really don't know anything about the process, because you're simply describing each data point with one input.
Right. Right. And then the other question I had is, getting started. I mean, any recommendations on, if someone's, new to this, thoughts on how to identify a good candidate, and just some direction on how to get started?
Yeah, sure. I mean, the best things to look for are items in your process where you know things are happening, you know there's changes happening, but you also know that you're not able to, for whatever reason, technical or staffing or otherwise, you're not able to measure those changes as often as they're happening. So whether it's a lab test or like I said, if you're working with an analyzer that's on a sampler and it's picking up 6 different samples, so it only gets around once every hour to that particular sample. Those are good. And then of course, like I said, you got to look at, do you have at least a good overview of measurements that are online and continuous to use as inputs to the calculation, because obviously the model is going to need some input data.
Okay, great. Well, those wrap up my questions, and I don't see anything else coming up in from the audience. So let's just kind of go here to the closing slide. And thank everybody for joining. And certainly, Scott, really appreciate you jumping on with us to walk through this demo. I think it was great to have a real world example and show off some of the features that are available through the Park model. So thanks again for joining us. And if anybody wants to get hold of us about more, here's a few ways you can reach out. And thanks again.
All right, thank you, Kevin. We'll
All right.
talk to you later.
Okay, bye now.